All right, now let's take a look at the probability distribution function, the PDF. It is based upon the histogram, and we saw it's 1 over n times the histogram. So here we have an expression, but it looks like algebra, doesn't it? You got this thing on the left equals this gizmo here in the middle, and we got the thing on the right. But we're dealing with sets. Holy cow, the set on the left is a function, actually. It's a set function. Histogram, and it's the PDF of a histogram. Well, that's still a histogram, it's still a set. So this PDF is a set, is equal to something, and it's the bins that we have, which is based upon X, and it's the histogram that we have here. And every member in that set, every bin in histogram is divided by n. See how easy that is? And the square brackets here indicate that the PDF is ordered. If you have squiggly brackets, curly brackets, instead of square brackets indicate an ordered set. In other words, you wouldn't have the histogram all laid out there in a random order. No, you start on 0 and you go to 1. All right, another related point here, which is important, so you're definitely going to hear this, is you're going to hear the whole concept of chance. It's an informal term, and it's really expressing probability of event. And by the way, I stuck another horse in on you. We've moved now from histogram and bin. That was our first horse. Here's our second horse, and that's the PDF. That's a probability distribution, and the concept of chance, which is a casual term for probability. What is probability? Now I got to get right down to it. Guess what? Just when you thought probability was going to be something useful or meaningful, and I got to tell you, I'm sorry. Let's just read what it is. What is probability? But we're going to have to get down here to the nuts and bolts. Probability. It's, while a term more formal than chance, yet it has a linguistic indeterminacy. And it is unquantifiable and untestable. It's commonly known as a mathematical measure of likelihood. Guess what? Over the last 200 years, scientists have been using probability, and the philosophers have been wrestling with what does probability mean, understanding the why of probability as opposed to the how of probability. Let's go back over this. And I hate to pop your balloon, but probability itself is a linguistic indeterminacy. Hey, you don't believe me? Click on one of your links down here. Take this one in the Wikipedia, indeterminacy. It's a philosophical point. Nobody knows how to truly, uniquely determine what probability is. Now, we saw in our very first presentation that the universe, starting with the Big Bang, is statistical. So we've marched right through this. If it's statistical, it's going to stand for probability, but we don't even really know what probability is because it's unquantifiable and untestable. But it's a measure of a likelihood, which means that it goes between probability is bounded between 0 and 1. Maybe you assign a chance for a known object or selecting an object, and it's indeterminate. The inverse of that measure of indeterminacy, of course, is 1 minus p. The objects can be purely random, and you can use that to test what is the universal statistical population behind something. You think it's random. You say this baby's bouncing all over. I don't know what it is. You can then statistically test, is it a Gaussian distribution? Then they have this type of a shape. But remember, this assumes that you've got an infinite number. This curve here, this nice smooth curve, is for an infinite number of samples. You don't have that many. You don't have time, and your boss isn't writing a big enough paycheck for you to wait around for infinity to count an infinite number of samples. So you have an approximation which has to be fit to this. Guess what? If you can make the very simple assumption that whatever I'm measuring are unbounded Gaussian distributions. In other words, they're boxcars. They're unbounded IID, independent and identically distributed. That's all. They're boxcar distributions, equally probable between 0 and 1. and you've got a bunch of those things. If you put them together and you add them all up, it's called the central limit theory. And the result is that it's the product of the probabilities. And Bernoulli process, amazingly enough, is the most random of all things. That means information transfer, the transmission of information, Bernoulli process. If you can control your messages to, rather than saying, the duck is green, and I like my duck, and the ducks are pretty, those are complicated messages, aren't they? But if you can say, yes, no, yes, no, that's Bernoulli process. And that is the most random looking at all. So if you're worrying about ciphers and cryptography and stuff like that, the closer you can make that message to look like it's not encrypted to anything. It just looks like purely random to me. In other words, it's undetected. That's probably the best crypto of all. Because the person on the other end has to know how to unfold that information that appeared to be statistics. All right, our third horse here is the CDF, the cumulative distribution function based upon the probability distribution function, which is based upon the histogram, and that's what it looks like mathematically. And given the PDF, the CDF identifies a central tendency of the statistical deviant. Parametric statistics assume a particular probability distribution. Normally, it's a normal distribution. Non-parametrics are those where you really don't know what the distribution is. It may be Gaussian or maybe Swahili. You have no idea. That branch of statistics, when you kind of wrap your arms around it, it's called non-parametric methods as opposed to parametric methods. Now, histograms themselves, commonly we treat those as bar graphs, PDFs, CDFs, and no matter where they came from, we generally draw those as smooth curves. Here's an example. This is a normal distribution in blue. And so we have our blue curve, our PDF here, ranges between 0 and 1, goes up and back down like that, centered around 10. So 10 must be the mean. Yeah, and then the standard deviation is 5 units right here. And then we have the CDF in red, the cumulative distribution, which is like saying, wherever you are, I'm going to add everything up to that point. And that then says that once we get to the peak, that corresponds to the 50% point, 0.5, which would be right there. And then it tails out. Once you've integrated the whole thing, you're way over here and you've integrated the whole information underneath that PDF. And of course, it asymptotically goes to 1, whereas the other end asymptotically starts at 0. And the mode, which would be at this 0.5 point, and the mean 10. And the median would also, in this particular case, also would be 10, standard deviation of 5. That's the starting point. We need to move on to quantization. That's our fourth horse. And in signal processing, it's the process of mapping our input values from a large set to output, which are a smaller set. So for example, here, we have original curve in green. The quantized signal is in yellow without noise, and then red is the noise. So people talk about the signal to noise ratio. That you can't really talk about signal to noise ratio with one value. This is the original value, that's the green, and that's the quantized value, and that's the noise. That's nice, but you have to express those statistically over a range, over a period of time. Yes, it does require time. And in a case like that, we're then able to describe the signal to noise ratio, which is an important thing here, that the quantization is time, and this is time sampling. In this particular case, we're quantizing in two different ways. We're quantizing in the senses that we're measuring something at a time sample, and we're measuring the curve at a time sample, but we're also doing it the other way. I don't know if you can see this very well, but there's some very faint blue lines here. I'm holding at the top one, the next one down yet, and these are the quantization values, and that is nearing the amplitude itself to the nearest bin value. And then the noise is also what is that third part in there. So you have quantization in time, quantization in amplitude. And so our seismic sample here at any particular time is to take a nice continuous seismic trace that we would use for our seismic data to help us find something that we can predict in terms of our geologic subsurface image, and then describe that in terms of bins. If we were to just make a black and white print, and we would have maybe little pixels here that might be, I don't know, 300 to the inch. If you make it 300 to the inch and then you just turn them on and off, it'll be so fine you'll never see the jagginess. If you say, I've got 100 bins or 100 pixels to the inch, yeah, you're going to start seeing jagginess. And if you set it to 50 or 20 or 10, you're definitely going to see the jagginess because you're rounding to the nearest bin. And if you're going to make and expose this on a piece of paper, this long one right here is the timeline this time, and here's the timeline at the next time. So these are the pixels that you turn on, and the baseline is the one right through zero, going between minus and positive values and then rounding to the nearest amplitude. So if you have a geophone over here, it's measuring a charge, which is a capacitor over a short period of time. In other words, how much current did it collect in that capacitor over a teeny weeny short period of time, maybe a microsecond, or it might be a millisecond. Maybe if you're sampling here, your sampling is collecting all the curve in that whole time sample interval right there. So whatever you're using, it's our estimate of voltage. And so we have, if we look at all the samples here, over the entire time, we have a probability distribution based upon a histogram of counts for the whole thing. And this is our amplitude distribution as a function of a histogram. And the number of samples near zero are this one right here, a lot of them. And these are the outliers, few of them. So this is like the peak of the peak, and the trough of the trough is over here like that. We have a continuous curve of floating point numbers right here. And after we have done the binning quantizer, and we run it through a quantizer, which is our fourth horse, the bin width is a change in the amplitude, and it's rounding, whereas the amplitudes themselves are continuous numbers, 6.21461 and 0.21202. Yeah, these are continuous values, and each one of those three get rounded. So these three right here get rounded to 6.21, rounded to the nearest tenth. Anyway, that's what a quantizer is all about, and here's our fourth horse. The histogram function sums over counts. Quantizer function creates a new signal. It creates a new something, whatever you had to start with. So the histogram quantizer is an excellent thing to sample. And the quantizer for a particular sample is indicated right here. And it could either be the actual rounded value, which is close to, say, an amplitude of a seismic signal, or maybe it's just the bin number. And that's the sample index that we would have. The quantizer function itself would be for a whole seismic trace, for example, could either be the samples, which are close to the actual samples you started with, or it could be the index. Now, because the bins, the histograms, are regularly sampled delta H, the quantizer is by necessity unbiased. And that's good news. We have then a methodology here of taking our seismic traces and running a quantizer on a 3D survey, and we can end up with something of value, which I'm going to show you in a second here what the value is. The important thing is that the expected value is unbiased because it sums over bin counts across the entire range of the whole 3D survey. This is a blizzard. This is a blizzard of mathematical notations, mathematical expressions. What kind of expressions? These are set notations. So we're dealing with sets, everything here from the cardinality. This is X is our sampled data set, it's sampled. We have N of those sampled. The bins, M, is how many histograms that we have. And that needs to be chosen. So N comes from the data set that we started with, and M comes from your head. Now you want to bin this thing and you want to make histograms, you got to choose M. And then it's a mapping operation. And we won't go through all this. I just gathered all this stuff together on one foil here so you can see everything, the 4 horses all the way from binning all the way through here to the quantifiers. Geology? Okay, I promised you. What is a geologic geobody? Think about it like this for a second. A geologic geobody is just a name. And give me the liberty of saying it is a name of something of uniform lithology. Okay? So this rock right up here, uniform lithology, it's a geologic geobody. How about the one over here? Yep. How about this one right under the one on the top? Whoops, it is too. Uniform lithology, uniform lithology, uniform lithology. Okay, so if you'll allow me that description of what a geologic geobody is, uniform lithology, and it allows us then to define something that of this picture right here. Geologic geobodies have some consistency. I can count, and so can you. I can take this rock right here, and if it's the same as that rock right there, our sample count is 2 of this particular geologic geobody. Okay, we have 2 geologic geobodies that have this lithology. We'll have maybe 1 of this geologic type, and then this one, this, and this. See, I break things down here by just imposing uniform consistency, uniform lithology. We've got something we can devote here to eventually some useful statistics. So here we got geologic geobody. And I'll just break down here what it could be. It's a uniform lithology and it's consistent. So uniform lithology is the buzzword there. Certainly a geologic layer of a, say, top particular formation. You got a formation above, formation below. It's a pair of top and bottom. That is a geologic layer which could be bounded by a pair of formations. Faults mark the lateral edges of geologic geobodies. It's the end of this thing, and it's the start of something different. Map edges. You get a geologic map. It's not a Mercator projection to the whole world. It might be in northwest Wyoming, for example, and you're doing some surface mapping in Yellowstone. Map edges, surface lateral edges, whether you want to think about it or not, but that's true. You don't know what's going on outside the edge of this geologic geobody. Mountains are deformed geologic geobodies. The rocks are upthrown. In this particular case, looks like they're pretty well horizontal. The tectonic, interestingly enough, guess what? I bet we could look at this right here and we see that they're pretty level. And we could probably say we doubt that the rocks have ever, from the time of deposition to today, they have not undergone any tectonic stresses to deform them in any way. And unless you had this weird case, they deformed, they got pushed laterally, for example, and they got squeezed one way, and then some weird thing, they got squeezed the other way in the vertical direction to unsqueeze them. Pretty unlikely. Mountains themselves, that's deformation. That's the structural features of still geologic geobodies. But they're not different. They're just changed. The shape of the geologic geobody is affected by the tectonic history. Other geobodies would be like cones, flows of volcanoes, mid-ocean ridges, caves, moraines, and meteorite impacts. Each one of these are geologic geobodies. Now, this is the end of our presentation. I'm so sorry we have to stop here, but we do. We have to stop. And we summarize things. The geologic geobody, it's a volume of rock of uniform lithology, and it's bounded by a closed surface. It's uniform rock bounded in all 3 dimensions, bounded by a closed surface. And it's often approximated by a closed set of seismic samples in a 3D survey. You got the Kawachika geologic geobody on one side of the fault, and then you got another Kawachika geobody on the other side of the fault. Same lithology, but they're two geologic geobodies, or the set of geologic geobodies. They're all the Kawachika, but now left of the fault, right of the fault. Now, what about the quantizer business? The importance of this presentation this morning is as a quantizer is a statistical method to estimate geologic geobodies. Holy Toledo, where does that sneak in on us? Here it is. You got a 3D survey. You got a seismic reflection traces. And that's like the third direction of every seismic trace is a map coordinate, right? X, Y. And that's how you end up with a cube, X, Y, T for time. Or you could convert the seismic trace from a time trace to a depth trace, guesstimate it some way, and you have a cube. Now, the seismic trace amplitudes, they measure the strength of reflected waves back up on the surface, don't they? And these traces, each trace is a continuous time series. The set of traces is also a set of amplitudes. Hello, here it comes. So the set of amplitudes of the seismic traces can be binned. That's our quantizer. Binned into amplitude subranges of a continuous trace, and now we're converting these to flattened steps. So what we have here then is that this is a peak, this is a trough, this duplication, here's another peak. So we have converted this to flattened steps. That quantizer is helping us classify samples by reducing that continuous data into flat spots, peaks, troughs. You can even have zero crossings as well. So the flattened steps that follow the peaks and troughs, they represent a horizon. And the horizon, top and bottom, with edges, that they represent geologic geobodies. That's it for now. Any questions? Anything you want to go back over again?
Yeah, Thomas Felix. So I had a question regarding a cave being a geobody.
Yeah.
Because it didn't seem to meet the definition of a rock, a volume of rock in a lithology. It seems to me like the edges of the cave would be part of some other geobody, but the cave itself is just an empty space.
You must be a hard rock man, Felix. Yes, I have mental waves from a hard rock geologist would also tell me, yeah, there's no rock in a cave. Huh,
No.
silly man, Tom. But hold on a second here. Is it uniform lithology? Well, maybe air. Is that uniform? Yeah, I guess it's uniform. But is air really rock? I'm about ready to poke you a little bit, Felix. And if you think about a rock, doesn't a rock have pore space?
Sure. Most of them.
Yeah. You got a good point. I'm just having fun with you.
Okay.
Anybody else? Thank you. Anybody?